It's a really complex socio-economic chemical problem, the problem of plastic waste. But we need to solve all these problems, right? Because plastic currently is polluting our oceans, it's filling up our landfills, right? And the status quo is not a sustainable way to move forward.
That status quo is what Dr. Frank Leibfarth is trying to change with his work on the chemistry of plastics as an assistant professor of chemistry at University of North Carolina at Chapel Hill. And it's what landed him on the Chemical and Engineering News's 2019 Talented 12, a list of brilliant young scientists taking on some of the world's toughest problems with clever chemistry. In episode 2 of this Science with a Twist series, Bringing Chemistry to Life, we speak with another member of the Talented 12 about their work and trends in their field. I'm your host, Paolo Braiuca, Senior Manager of Global Market Development at Thermo Fisher Scientific. We began by asking Dr. Leibfarth not about his postdoc with influential chemist Tim Jamieson at MIT or his Camille Dreyfus Teacher Scholar Award, but about a different accomplishment from earlier in his career. As a junior place kicker on the University of South Dakota American football team, he secured not one, but 3 USD kicking records.
A few years ago, somebody passed me. So I'm now the second all-time leading scorer. But it hurt a little bit when somebody passed me, but the thing I was happy about, it was another kicker, and I was a kicker, so we all stick together. So in the end, I'm happy for him, and records are made to be broken. But no, that playing football was a fun, ephemeral, and now in my position, it feels like another life ago.
So I guess being a kicker gives you an edge in terms of being an all-time leading scorer?
Sure, yeah. Every time the team scores a touchdown, I get to go and get a point, right? One of the things is I played a number of years. I ended up playing 3 years there, and we had a really good offense. So I benefited from that, and it was kind of the accumulation of points over time that got me there.
So I'm glad you were a kicker, because that's the only position of American football that Europeans understand. How does a record-scoring kicker become a high-profile scientist?
That's a good question. I often ask myself that. I grew up playing athletics. If you would have asked me what I was going to be when I grew up, when I was a kid, I think the last thing I would have said was scientist. I grew up in a small town in an area that was dominated by agriculture. I didn't know any PhD scientists growing up. I didn't really meet them until I went to college. But I always knew I liked to make things. My dad kind of had a side job as a carpenter. He drove a semi-truck otherwise. And I love going and making things with him. But I also love the intellectual aspect of school and education. Even though I didn't know it, I was trying to figure out a way to combine those things. And it was after my sophomore year in college, I really wanted to travel, but I didn't have much money. And I couldn't spend a whole semester abroad because I played football. So I was kind of in this pickle. And I asked my organic chemistry professor, hey, is there a way I could travel somewhere but still get paid for it? And, do chemistry because I liked your class. And he pointed me to these National Science Foundation REU programs. And I think I applied for 10 of them and got rejected by 9 of them. But the one I got in was at Columbia University. I went from a town of 10,000 people to a town of 10 million people. Was overwhelmed by everything, the science, the city, but really found my passion in the lab. I love the intellectual atmosphere. I got to make things because I was doing synthetic chemistry. So it kind of combined all the things I liked. From then on out, I was committed to the career.
Okay, let's jump to the most recent years, right? And let's try to position you somewhere in the chemical science. So am I correct if I define you as a polymer chemist?
Yeah, I say I self-identify as a polymer chemist.
Would you recognize yourself as an organic chemist in any way?
Sometimes I get labeled as being an organic chemist. Definitely a synthetic chemist. We do in my group a lot of organic chemistry, I would say, and synthetic chemistry. But really the innovations we're seeking to make are in polymer science and in polymer chemistry. So that's why I think I clearly fit in as a polymer chemist. But that's one of the great things about polymer chemistry and polymer science in general is it's inherently interdisciplinary. It sits kind of at the interface of all these different disciplines, and you get to put on different hats depending on, who you're talking to or what day it is.
Can you tell us a bit more about the lines of research that you're currently pursuing in your team?
So I like to say our lab is not so much problem-driven, but it's really driven by the chemistry, and the chemistry we find interesting and we want to pursue. So the application space we're pursuing is actually pretty vast, but it really distills down into a few fundamental chemical innovations we're seeking to make. And the three of those broadly that I would say we're focused on, the first one is stereoselective polymerization. So that's trying to use the tools of asymmetric catalysis to control the stereochemistry during polymerization, and then ideally, right, identify valuable material properties from those new materials we make. The second is in polymer CH functionalization. This is taking the polymers that we make on millions of tons scale that, most people, and truthfully myself when I was going through my education, kind of found boring. And actually trying to make them interesting through really powerful but selective CH functionalization techniques, where we can take these really strong bonds in the polymers, modify them, and ideally our focus right now is using those to upcycle these really high volume polymers, and in the end upcycle them to the point where they can be reused over and over, so actually improve their recycling at the same time. And the third area is really on the interface with chemical engineering and polymer chemistry, and that is using continuous flow technology to automate polymer synthesis, plug that into making large libraries of materials, using things like artificial intelligence to help guide our synthesis, and discovering material properties that seem counterintuitive by being able to really probe large structure spaces.
Let's start from your work on the stereo control polymerization. That was what won you the consideration for the Talented 12, if I'm not wrong. And I was reading your extremely interesting paper you published on Science. Congratulations for that, by the way. Polymer isotacticity is not really a new concept. So what is the real innovation of your work there?
Yeah, it's not a new concept at all. Julio Nada won the Nobel Prize in, I believe, 1963 for discovering or defining what an isotactic polymer is and discovering isotactic polypropylene. Isotactic polypropylene is made at over 60 million metric tons. It is the largest application of a stereoselective catalysis in the world. But since the time of Nada, and he found the same problem. The mechanism through which you make stereo-controlled alpha olefin polymers is this coordination insertion mechanism. And the problem since then is if these are usually using early transition metal catalysts, and if you add any Lewis basic component into that polymerization mixture, it will shut down catalysis or inhibit
because it binds strongly to the metal, I suppose.
Exactly.
Right.
So I guess the story of kind of how we came up with this project really started from just a fundamental interest. Ben List came and gave a talk at MIT when I was a postdoc there and talked about these really beautiful catalysts he was making that were chiral counterions. I just was really inspired by that talk and thought, I wonder if I can do the same thing with polymers. So it started kind of from that pretty naive place. And I did not have any experience in asymmetric catalysis in my training. I built the idea from there to identify a polymer class that was of interest that really the stereo-controlled polymerization of that hadn't been solved yet. I identified some properties that I thought would be really interesting if we were able to control the stereochemistry of those polymers. Nature's ability to control the structure of biopolymers, everything from their sequence to their stereochemistry to their length, is exquisite. There's a long history of polymer chemists being inspired by that and moving towards that. And I think stereochemistry is one of the areas that has been underdeveloped in polymer science. We're pretty good at controlling the length of polymers. We're getting better at controlling the sequence. But the stereochemistry, especially of polar polymers that have these Lewis basic sites, is really a big challenge, and I think area of the field that is really open for innovation in the near future.
So you've got the inspiration for this ionic polymerization from the work in a different field of chemistry.
Yeah, absolutely. I've been talking to my students a lot about this. Like, there's a question in science, right? How do you teach creativity? How do you teach somebody to be creative? It's kind of like one of the large existential questions that I don't think anybody has a great answer for. But I've identified how I'm creative is I have a deep knowledge in polymer chemistry, right? That is my core discipline. But I try to learn as much as I can about fields that are kind of tangential to polymer chemistry, and really look for the places where those fields intersect. And then obviously with my core expertise in polymer chemistry, I think it's important then once, right, we are able to make an innovation, we can actually go and characterize those materials and see what they're good for. So in that stereoselective polymerization paper, we didn't just do a stereoselective polymerization. We then actually made films of those materials. We pulled on them until they broke and saw how strong they are. We saw how adhesive they were, right? So we can then take those fundamental chemical innovations and relate them to properties engineers really care about.
Am I understanding correctly, Frank? You're using ionic polymerization in this application will open you the opportunity to look at sort of different types of monomers for your polymers, things that are slightly different than the traditional oil feedstock.
Yes, very good observation. One of our real goals as we develop this catalyst is to use feedstocks that are derived from biorenewable resources, right? Things that we can derive from lignin or sugar or other natural resources like that. What nature loves to do is oxidize things, right? And that really doesn't fit with kind of the classical coordination insertion polymerization that makes petroleum-derived polymers. In some ways, coordination insertion polymerization are kind of the bedrock technology for polymer science in the last 70 years, is perfectly suited for petroleum-derived products. But we really need to rethink that catalysis if we want to start making plastics from renewable resources. So we need to create polymerization techniques that are amenable to the oxidation processes that nature loves to do. Usually you have highly functional products that come from nature. Can we develop selective polymerization processes to use those products? So yeah, you're spot on in that observation.
So the future is going to be potentially from relatively simple, small hydrophobic compounds to fairly complex multifunctional ones as monomers that could potentially lead to completely different final products with completely different properties?
The scale these things are made at is tremendous, almost unimaginable. If you're just sitting there trying to picture how much synthetic plastics are made per day, right? It would probably fill the building you're in, if you're in like a large building. These things are made, they're shipped by the rail car. More than 1 million tons of plastic is made per day, and that's a lot of plastic, right? Because of that, it's going to be a combination of everything. I think there will be a large role to play for completely new materials from biorenewable building blocks. Ethylene and propylene is actually a byproduct of petroleum refining. So in some ways, that's a waste product that we kind of have to get rid of, and the best way to get rid of it is to solidify it. And of course, then we can use that solidified product, right, as something. So I think the important thing to do is, right, most of the polyethylene and polypropylene, those petroleum-derived polymers we use are single use. And I think that's where we have to start moving away from. Can we also develop new chemistry to extend their use beyond single use, right? And ideally that we can start reusing them.
So do you foresee a world where plastics will be chemically completely different materials?
I think some plastics will be completely different materials, and some will be modified from what they are now. And then there are some applications that are really high value and just really, really important. I can think of things like sanitizing medical equipment, right, that we want to ship around the world to places maybe that can't effectively clean medical equipment. And when you open that syringe to give somebody a vaccine, you need to know there's no bacteria in there, it's completely clean. It's probably worth using the best polymer for that job, even if it may be single use. But your milk jug that you get from the grocery store, if that's a completely different material that can be recycled better, that's probably good. Or the plastic bag you get from the grocery store, right? So it's a really complex socio-economic chemical problem, the problem of plastic waste. But we need to solve all these problems, right? Because plastic currently is polluting our oceans, it's filling up our landfills, right? And the status quo is not a sustainable way to move forward. Money tends to talk, right? So if you can create something that is more valuable than the original material, I think that will catalyze a larger incentive for actually recycling materials, right?
And it's very clear how your work in this direction is supporting real life application and particularly for remediation and environmental pollution and waste treatment. That's very clear. And I want to take a segue from your saying that some of the plastic will just need to be functionalized in a different way. So speaking about the CH functionalization, can you tell us a bit more on how you go along that kind of work?
That work was originally inspired by some work I did in graduate school. I published a paper in graduate school that allowed me to cross-link polyethylene. Well, there's two main applications for cross-linked polyethylene. The first of which is actually the piping that is starting to replace copper that goes from your hot water heater around your house because it's nice and thermally stable, usually called PEX tubing. Another big application is in replacement joints. A lot of replacement hips, the cup is made from ultra-high molecular weight, cross-linked polyethylene. But right now, those are all cross-linked in kind of a really messy, radical process, usually using gamma irradiation, so really high energy. In graduate school, I was able to collaborate with Guy Bazan and my advisor, Craig Hawker at UCSB, University of California, Santa Barbara, and we were able to take a bottom-up approach to cross-linking polyethylene, where we're able to add in these unique monomers that then underwent a secondary reaction that created a more thermally stable polymer. But then when I got into my current position, that project that I had done 8 years earlier kind of came back to be really valuable because I was in a oral exam of one of my colleague's students, and she had just this really powerful reagent that could functionalize CH bonds, aliphatic CH bonds, really selectively, and she was using them to do late-stage functionalization of pharmaceutical compounds. And I told her during that meeting, and then my colleague, her advisor, that could really work on polymers. And there's this problem in polymer chemistry. Every time you try to cross-link these branched polyolefins, right, you have to use these really harsh conditions, and you end up getting a bunch of side reactions, and it's just pretty messy. So we started working together. We developed a method that was really selective for polyolefins. It's a radical functionalization process, and we showed that we could do that to isotactic polypropylene within a reactive extruder. So a reactive extruder is essentially kind of a big oven that pushes polymer through with a screw, so you can really mix through shear high viscosity materials. So that selectivity had not been seen in metal-free type functionalizations. And we now are thinking of ways to use that to compatibilize polymer blends that are otherwise really difficult to separate in recycling streams. So in recycling streams, polyethylene and polypropylene, for instance, they have similar densities, and if you just melt them down and blend them, they have really poor material properties. We're thinking, can we develop a method where if you just take that blend, sprinkle in a little bit of our reagent, can you now get out more interesting thermoplastic properties and actually be able to use that material mixture?
So reading your Chemical Science 2019 article, seems like you're using photocatalysis as well. That's quite interesting. It seems to be a hot topic at the moment, maybe not in polymerization science, but in other fields of chemistry. Am I right?
Yeah, photocatalysis is really unlocking interesting chemical transformations that a lot of people thought were impossible for a long time or could be done with other means that were far more complicated. Actually, after conceiving this first project that I talked about on the CH functionalization of polyolefins, my group started thinking more broadly, like, well, could we CH functionalize other polymers, and how would that be useful? And we identified this photocatalytic method that was originally reported by Corey Stevenson. He's at the University of Michigan. And so we started testing that, and we found out that we could add these fluorinated units to polystyrene really efficiently. And you could use commercial polystyrene. We actually even showed that you could use post-consumer waste polystyrene. So if you just take like an old styrofoam cooler, chip off a little bit, that was just as effective in the reaction as a pure feedstock. And that was good, and we had for a while a collaboration with industry who was interested in some of those materials. Another interesting route to possibly upcycle polymers, make them more valuable than the initial material to create that economic incentive to reuse otherwise single-use plastics.
Polymer science has been around for a lot of time, several decades now. And yet the innovation that you're bringing into the field seems to be coming from your ability to get ideas from other parts of chemistry or maybe from collaborations with other scientific disciplines. It's really inspiring.
I often tell my students, this term is used kind of in business a lot, to be T people, like capital T. So what a T person is the downstroke of the T is your deep expertise in one discipline. In our case, that's polymer chemistry, right? I'm a polymer chemist. The students that come out of my lab will be trained in polymer chemists. I want them to be really knowledgeable in that. But the horizontal aspect of that large T is your knowledge in all these other disciplines. I would never call myself a biochemist, but I love to go to my biochemistry colleagues' seminars and try to learn something and try to pick up little tidbits, right, that I could bring back to my own discipline. And if you can have an expertise in that, but a curiosity about other fields and where they can make a difference, I think that's a nice pathway towards being creative and making impactful contributions.
That makes me very curious. You mentioned the use of continuous flow to generate these libraries of polymers. And that's an interesting concept when you think continuous flow and polymers being solid materials. How does that really work?
Many plastics are solid at room temperature, but if you heat them up enough, often they flow and you can shape them into different parts, right? So that's what we usually call thermoplastics. Actually, most polymerization processes are done in some kind of continuous fashion. Polyethylene, for instance, ethylene itself is a gas. So often, right, this is a gas continuously flowing over a catalyst that then creates that solid polymer. And there are numerous different ways that have been engineered to isolate that. Continuous flow technology, in a way, in polymer science isn't new, but I think there is a place to do this kind of what I would call intermediate scale continuous flow technology, where you have really discrete control of all the different variables that could go into making a complex product. And if you can do that, and if you can automate it, you can start to make large libraries of materials pretty easily. And there are, I think, a lot of challenges in polymer science that we haven't started to tackle yet, just because they're so complex. When you start adding lots of different ingredients to a polymer, kind of like when you started adding lots of different ingredients when you're cooking, you never know what's going to come out, right? You might taste it, it might be fabulous, and you might taste it, you might be like, whoa, I never want to do that again. So when you start making these large libraries, right, you get into the structure space and you have all these variables, they're interdependent, so oftentimes you can't predict a priori what's going to be the best material. So if we have an easy way, a user-friendly way to make these large libraries, maybe we can start to discover, right, those materials that can solve really challenging problems in kind of this haystack. It's kind of the needle in the haystack approach.
So is the long-term goal having a sort of tool set or toolbox to be able to explore systematically the accessible chemical space for any given combination of monomers and trying to get to all the possible different combinations and see the correlations with their functions?
Yeah, absolutely. And we really do see this, once we're able to build it, we see it as a platform where, right, we would have the tools to make all these things. It's kind of like an automated peptide synthesizer, right? Maybe someday we'll even get to the point where, right, other labs could buy, right, this tool and then use it to solve the problems they want to solve. So if we can start to make these systematically, as you said, if we can make it so, a non-synthetic chemist can operate something like this. I recently won the Beckman Fellowship, and Arnold Beckman had a really inspiring vision, and his vision was, he makes tools that then other people can do science with. That's our goal with the continuous flow work, is to put those tools of polymer synthesis that I think are really valuable, because I'm a polymer chemist, into other people's hands and allow them to explore structure spaces.
How far are we from having this platform ready?
So the first application we're targeting is making some MRI imaging agents. And we started with 6 different monomers. So the total structure space we could possibly make when we combine these monomers at 5% increments is about 65,000 materials. And again, these display interdependent properties. So you add a little bit of one monomer that increases one parameter, but then lowers another parameter that you're interested in, and it's back and forth, and it's hard to figure out. So now we've developed an instrument that can make one individual polymer sample every 2 minutes. We've now made over 250 samples. Right now, the machine, from selecting starting materials to synthesis, is all automated. So my student just types all, he now built this instrument, so he types all this the information, the materials he wants, into an Excel sheet, uploads that Excel sheet into the software he has, and pushes go. Right now, still, we have, one of the big challenges is automating purification and automating characterization. We can do that for some properties, but for really interesting properties, I would say that is still a work in progress.
It sounds to me you're not that far, which is very exciting. So I really look forward to speak to you again in a couple of years, and you'll tell me about this beautiful final platform and how it works and what you can achieve with that.
I hope so too.
So as we're coming towards the end of our chat, let's speak a little bit about your sort of small daily technical and maybe personal challenges you face in your work, the things that you need to deal with on a daily basis, you and your team.
There's a lot of things to deal with, and then a global pandemic started. So now there are even more challenges to deal with. I'm not too far away from starting as an assistant professor. I just celebrated my 4-year anniversary at UNC, so I'll put it in that context. Building a lab has been the most exciting and most challenging thing I've ever done. The most important thing that I identified at the beginning, and I would say is still the most important thing, is building a positive and innovative lab culture, right? Because everything stems from some of the, we have some of the smartest students in the world coming to UNC, and, they're excited about chemistry. They want to innovate. So how do you keep that spark alive while they're going through a growth process personally that everybody goes through from the time that they're 22 to 28, when they start to focus on one problem really intensely and have failures and deal with challenges. So that has been a big challenge, but that's been a really fun challenge. That's really hard to begin with, both from the student perspective and from my perspective, figuring out how to manage these people the best, figuring out how to fund them through different funding avenues, also learning to teach and everything at the same time. But having this all upended by COVID and having, stop research and then start research and have so much uncertainty around this has been especially challenging for my students for their research progress. They still want to graduate on time. They're still looking to get jobs, but their resumes are going to be significantly hit. The same goes for me as an assistant professor. It's been challenging for their mental health. I have a 10-month-old. It's been challenging just technically trying to figure out childcare. It's been challenging for my mental health, dealing with all these things that are coming at me when the job of an assistant professor is already difficult. I would never trade this job for anything. The ability to be creative and work with excited young people is super fun. I never thought I'd have a job this fulfilling as I was growing up in South Dakota. That really always was my goal as I was growing up, is I want to have a job that's isn't horrible to go to. My dad drove a semi for many years when I was growing up, and he never complained, but it was very obvious he didn't enjoy getting up at 4 a.m. every day and getting in that truck. So I saw him and I was inspired by him, but also knew my goal in life is to not hate getting up in the morning. And I've achieved that goal for sure.
I can only give you my congratulations. And I'd like to ask you one final thing. You're a very accomplished and successful scientist, despite your still very young age. And I'm sure you have a bright future ahead of you. What's one piece of advice you'd pass on now to a young chemist or scientist just starting their career?
I think the biggest thing I can say is trust yourself. You will get so much different advice. You will have imposter syndrome. You will see all these other people successful and feel like you're being left behind. But in the end, you go through all this training. You, in many ways, commit large portions of your life to educating yourself in science. It is a calling for those who are committed to it like that. You know best. Definitely get advice, Lean on mentors. That is really important. But in the end, when it comes to those make or break decisions, you know best. The thing I think of is pursuing kind of this research area on asymmetric catalysis. I didn't have any experience in asymmetric catalysis. I asked some people and they're like, that seems pretty risky jumping into that area. It's not for the faint of heart. But some part of me knew that there was something really interesting down that road. And I guess another piece of advice goes along with that. Once you get a job as a professor or in industry after your PhD, that does not mean you're done learning. You actually just learn faster. Trust yourself and embrace that continued learning, because you can continue to get better. And those skills will just keep building, right? It's not like you lose any of the skills you've built over those years. Take the swings, and sometimes they work, sometimes they don't. Everybody's career is different, and the nice thing is there's many different definitions of success in science. If you're committed and if you're flexible and if you trust yourself, it'll probably work out.
That was Dr. Frank Leibfarth, Assistant Professor of Chemistry at UNC Chapel Hill and one of the Chemical and Engineering News's Talented 12. Thanks for joining us for this episode of Bringing Chemistry to Life, a Science with a Twist series. We'll bring you more conversations with the Talented 12 every other week. For new episodes, subscribe wherever you get your podcasts, and you can visit labchemresources.com for more information about Thermo Fisher Scientific laboratory chemicals. This episode was produced by Matt Ferris, Gabriel Lorama, and Emma Jean Weinstein.